Hello, kind people. How are we doing today? Good, good. All right, cool. Let's go ahead and get started. I'm trying to get to the 4.3. I doubt I'm going to get there, so no need to worry about it. There's only one announcement, and that is the test on chapter 4, the unit 2 test is going to be next week, Wednesday. So for that test, you're going to need to bring your computers to class, and we will take the test on the internet machines. Any questions before we begin? All right, cool. Last time on Inspector Gadget, we almost finished off 4.2. And 4.2, your rules of probability. You do addition when you have an or. You do multiplication when you have an and, i.e., when two things are happening together. And then your conditional probability is a probability given something else has already happened. Yes? The classic example is pulling a ball out of a hat, right? If I have 10 balls in there and I pull out a blue ball, the probability of getting another blue ball is going to change, correct? Because there are less balls in the hat and there is less balls in the hat. Yeah? Yeah? All right. So let's look at there a little bit more of conditional probability. And we will start right here. Again, here's the notation for your conditional probability. The probability of B given A. This question is actually asking, what's the probability of B? But they're saying, not only am I asking you this, I am telling you something. I am telling you something. That thing is your A. So it's said, what's the probability of B given that A has already happened? What's the probability of pulling a blue ball given that the first ball was not blue? Yes? And that's what your conditional probability is. What's the probability that a man, selected male, is 6 feet tall, 6 feet or tall or higher, given that he plays basketball for a living? Yes? Questions there? All right. We had our multiplications. And so we had the example of a king and a king. So if you're drawing from a 52 card deck right here without replacement. When you have without replacement, it means the events are dependent. The first card you draw is going to be a king. What's the probability of getting what's the probability of getting two kings? Well, on the first draw, it's going to be 4 out of 52 chance of getting a king. But the second draw, that's not going to be the same, correct? Because there are less cards in the deck. In particular, there are less kings in a deck because you already have one king. Yeah? No? Maybe? And so the second king is going to be 3 out of 51, 1 out of 17. And so therefore, to find the probability of getting two kings, the probability of getting a king, multiply probability of getting another king. And that gives us 1 out of 221. Questions there? This actually is the same for any of the face cards. So the probability of getting two kings, two queens, two jacks, or two aces. Actually, for all the cards, the same 1 of 221 chance. Getting exactly the same two cards. All right. The interesting thing right here are the combinations. So let's say you're playing 5 people, yes? Your first card you got is a king. What's the probability that you get a king the next time around? Right? You're not the only one pulling cards from the deck, right? So, right? So 5 more cards are going to come out of the deck before you get a chance to pull, right? So the probability is going to be a lot more complex, yes? And then you have to imagine what happens if somebody else has a king as well. So now there are only 2 kings left in the deck. Yeah. Doesn't that stuff just make you happy thinking about all the possibilities and the combinations and the trials and the errors? No? No? Because one of the big things right here is, let's say I don't even know about gangling, but let's say the 3 cards in the deck, you have 2 kings and then you see a king on the deck, right, on the deck, or that's three kings in total, that you have to do some serious calculation to figure out whether or not that fourth king can come down or not. And you have to look at how the other people play. If someone else is playing, that maybe they have a king as well. And all right, let's just calm down here. Let's just not get too excited. All right. Example, conditional probability. We'll stay here for a little bit right here. If one person is selected, right, describe the probability that the person is male, given that person is never married. Let me underline the question right here. It is right, it's asking right here, what is the probability that the person is male, given that that person is never married? The first thing I want to ask you right here is, how do I write this down? Is I write down this way? Probability M, or do I write it this down? Which is the right way to state the problem using probabilistic notation? Is it A or is it B? I have two people saying A. Anybody else wants to contribute? All right, let's do it a different way. If you think it's A, raise your hand. If you think it's B, raise your hand. If you think it's C, raise your hand. The correct answer indeed is A. But I am asking, what's the probability that the person is male? That is what I'm trying to find. What's the chance of this person being male? But I'm saying, hey, don't look at all the male people. Only look at the people who are never married, because I know that this person has never been married. All right? Anybody wants to tell me what the answer to this question is? What's the probability of selecting a male person given that they're never married? Anybody? 40%. The correct answer indeed is that there are 40 men who are never married out of a total of 75 people who are never married. The key thing right here is, you see how he's saying never married right here? It means I am looking at this column only. Given the fact is this person has been never married. In other words, we don't care about all of the other areas. Does that make sense? That make sense? And so then probability of being male is 40 out of 75. Questions there? Questions there? All right. So they have it for us right here. Find the probability that you're male given that you're never married. That's going to be 40 out of 75 or 8 out of 15. All right. Find the probability of this. So, probability that you are female given that you have been widowed. What's that probability going to be? What's the probability of being female given that you are widowed? What's that probability going to be? The correct answer has been given. Indeed, it is 8 out of 12. Let me pause. Anyone not sure how we got 8 out of 12? Because I'm about to bend your brains. Any questions? So your brains get bent. Any questions? All right, everyone's sure that's the right answer, yes? Because it is. So what's going to be the answer to this? What's the probability of being widowed given that you're a female? What's that going to be? I have one person saying 12 out of 131. I have, what did you say? 12 out of 131. Anybody else? You look like you disagree. Go ahead and say that loud. 8 out of 131. Anyone else? All right, cool. So the given is that we're only looking at women, correct? So these are the one we're looking at. How many women are there? There are 131 women. How many of them are widowed? So the answer is 8 out of 131. Questions? Question? Question? All right, then, okay, that means I need to try again. You're looking at me funny. That means I try again. What's the probability of never being married given that you are female? Anybody else want to say an answer? Anybody else want to give an answer? People in the back. In the back. In the back. In the back. Anybody back there want to give an answer? So again, you start right here with the restriction. We are only looking at women. So it means we're only looking at this part of the table. Yes? So the total is 131. How many of them have never been married? 35. And so that's the probability, Ibrahim. What's the probability of being female given that you have never been married? What's that going to be? 35%. It is going to be 35 over 75. I am paused. Questions there? Questions there? Yes. Oh, there's a reflex action. Sorry. Reflex action. Sorry. All right. All right. Y'all still looking at me weird. So let me try again. What's the probability of being female? What's the probability of being female? It is 131 over 251. Is that okay? Is that okay? What's the probability of being female given that you are divorced? What's that going to be? How many people are divorced? How many of them are female? So it's 20 out of 30. Questions there? You feel a little bit better now? You feel a little bit better now? All right, cool. I can step forward then? All right, cool. Skip. All right, so that's not the end of 4.2 just yet. Mutually exclusive events. Do you guys remember what mutually exclusive events? We already did those. Remember what is on the board? What's a mutually exclusive event? Two events that cannot occur at the same time. Yes? All right. And remember, when we have mutually exclusive events, this goes away, yes? Probability of A and B is 0. Probability of A not 0. Okay, yeah. All right. And then, anybody remember what dependent events are? What's the dependent event? Two events that rely on each other. If one thing happens, it changes the probability the next thing happens. Yeah? Yeah? For example, if I get a king, the chance of me getting a king again changes if I am not putting the cards back in the deck. Yes? So they're dependent on each other. Okay? I think they're just giving us everything over again. I think we talked about with and without replacement already. Sampling with replacement, is that dependent or independent? Is it dependent or independent when you're sampling with replacement? It's independent, right? Because what happens is every single time the deck goes back to 52 cards, yes? Because I'm putting it back in there, yes? Well, without replacement, that's going to be dependent events. Because every time there are less cards in the deck. Yes? Questions there? All right, and so we already talked about these already. What's the probability of someone not being divorced? Okay, you have to do the math in your head. Tell me what to do to find the probability of a person not being divorced. So indeed, the total number of people is going to be 242, and we have to enter right here how many people are not divorced. Yes? And so it means we have to take these people, and these people, and add them all together. Yes? So that's 204, 228, no, 218. And so that's going to be they divided by 2. I had 218, so they divided by 2. But any questions there on the not part? Any questions there about the not part? All right, cool. I think that's it for us. already. I think that's it for us. All right, cool. All right, so that takes us to our last section for the test, and that is 4.3. It's definitely not 4.3. Trees and counting techniques. We have already done trees, so this will be a little bit of a reminder, the trees part, but the counting techniques will not be. All right. A tree diagram is the one that we've seen before right here, where you start with a node and the nodes expand as we have more choices. Yes? Remember we did the example way back when, where we had to have the boys and girls figure out how to write out the families, and we draw a tree. First node, boy and girl, and each one split from there. Yes? Excuse me. Jade is in a nursing program and is required to take a course in psychology and a course in psychology, physiology, and I'm missing Spanish. Where is the Spanish? Oh, and Spanish as well. So those three classes you need to take. There are two sections of psychology, 2 of A&P, and 3 of Spanish. How many different class schedules can Jade choose from? Okay. If we want to use the FCP to solve this problem right here, how many options does she have for psychology? How many choices can she make for psychology? 2. How many choices can she make for A&P? How many choices can she make for Spanish? So then how many different choices can she make? How many different class schedules can she choose from? Do we add all the numbers up? We multiply all the numbers together, yes? And so 2 times 2 is 4, 4 times 3 is, and so she will have 12 class schedules to choose from. Questions there? Yeah, so the next time you're going up to select your classes, it's going to go through your head. How many different options do I have here? You can figure it out. A different way to represent this is through a tree. Now again, if I take a tree right here, you have your starting node. And then what happens is psychology, there are 2 sections. And so from your starting nodes, you can either select section 1 or section 2, yes? Then after she's made her selection for psychology, she'll have 2 selections for A and 2 choices for A and P. So again, for each node, there'll be 2 choices. I can either do section 1 and then section 1, or I can do section 1 and section 2, yes? And down here, there'll be 2 more nodes as well, yes? For a total of 1, 2, 3, 4 nodes, 2 times 2. Right? 2 times 2 is 4. But then there are 3 sections of Spanish, and so then she'll have 3 choices, 1, 2, 3, from each of these nodes. 4 times 3 gives us a total of 12, and so she'll have 12 possible course selections. All right? Questions there? For example, she can choose to have section 1 in psychology, section 2 in A&P, and section 3 in Spanish. And that's one possible class schedule that she could have. But then she realized, wait a minute, I want to go to work. So this class is too late in the evening, so I'm just going to switch to this section instead. Right? That's what we do, yes? We had our selections, but wait a minute, this is happening. I want to switch my schedule. She can switch to a different schedule. Questions there? The point is the tree is a way to visually see her options. The only problem is what happens if you have 64 options? Who wants to draw a tree for that? Yes. No. Maybe. Anywho, I digress. All right. We talked about those already. All right. So that takes us to our 2 big things we need to cover for the rest of the section. One is called a permutation, and the other is called a combination. Anyone ever heard of permutations and combinations? A permutation is the number of ways you can order something. Right? I have to select one class, I have to select another class, I have to select a third class. Permutations is the different ways these things can be ordered, which is going to be in first, which is going to be in second, which is going to be in third. Okay? Now, think of it in terms of this right here. Let's say I'm having a horse race. That's the classic example. I cannot draw a horse. I do apologize. But my horse race is very simple. There are only 4 horses taking part in this race. How many horses did I say are taking part in this race? 4. I can ask the question, how many different ways can they finish the race? How many different orders can the horses finish the race in? I can ask that question, yes? Right? So that means someone is going to finish in first place. Someone is going to finish in second place. Someone is going to finish in third place, and then someone is going to finish in fourth place. Yes? So let's do a little bit of trial run. In other words, how many times can we run this race and then have a different order? That's a different way of asking the same question. How many times can we run this race and have the horses finish in a different order from before? That's a different way of asking this question. All right? So let's run through the analysis. The race has started. The horses are galloping. They're basically neck and neck. Yes? When someone finishes in first, how many options do I have to choose from? When someone finishes in first, how many possible options are there for someone finishing in first place? There are 4 horses, so there's 4 possible horses that can finish in first place. Yes? So I'm going to put a 4 right here. How many horses can finish in second place? 4 horses cannot finish in second place, because someone has already finished in first. Yes? So the possibility has to be there are 3 choices for second place. What about third place? How many horses can finish in third place? Only 2 horses, because someone has already finished in first, someone has already finished in second, so only 2 left. And how many options are there for fourth place? There's only one option, one chance, right? Only one horse will finish in last. No matter how you run the race, only one horse will finish in last, because the other 3 had already crossed the line. Yes? So the question then is, how many ways can we order these things? And we can use the fundamental counting principle. I simply need to multiply these numbers together. 4 times 3 times 2 times 1, and that will give me the number of ways these things can be ordered. 4 times 3 is 12. 12 times 2 is 24. There are 24 different ways these 4 horses can be ordered. Questions there? What happens if I had 5 horses? What would happen if I had 5 horses? This would become second place, yes? And have a 5 in front. And then the answer would be 5 times 4 times 3 times 2 times 1. Yes? That's 24 times 5? 120. What happens if I had 6 horses in a race? That'd be 6 times 5 times 4 times 3 times 2 times 1. Yeah? That's going to be 720 possible outcomes. Do we want to go for a 7? Aren't you glad you get to use a calculator? But yes, so the number of operations, the number of permutations, as we say, the number of ways they can be ordered is simply multiplying down, cascading. 5, 4, 3, 2, 1. Multiply those down if I have 5 people in my race. All right. And so because of this right here, we refer to a group of n items. N is the number of things you're trying to put in order. In my example, that was 4 horses. Yes. And with that right here, we have this thing right here. Your permutation is found by multiplying numbers in order. Mathematicians recognize that we have to multiply numbers in order a lot, and so they created a mathematical notation for it. That notation is called the factorial. You guys ever seen it before? Look at your calculator again. All of a sudden you see an exclamation mark in your calculator. It actually has a use. It's not just you trying to tell the calculator you're happy to see it, right? And so, for example, and so, for example, 5 factorial will be 5 times 4 times 3 times 2 times 1. In other words, this is actually saying, hey, if I have 5 different objects, I'm trying to tell you how many ways they can be ordered, the answer is going to be 5 factorial. Questions there? A small side note, by definition, 0 factorial is not 0. 0 factorial is 1. It's something that you need to remember, or just ask your calculator. It'll do it for you. But it's one of those little things that throw students off the definition. It makes a lot of the formulas look pretty. So therefore, it must be true. Oh, no. All right, somebody help me out. Break out your handy dandy calculator, look for the factorial button, and see if you can find 10 factorial for me, please. Break out your handy dandy calculator. Just about all calculators have it these days. And see if you can send me the answer to 10 factorial. What does excited 10 mean? Don't do it by hand. Don't go 10 times, 9 times, 8 times, 10, 6. Don't do it that way. I just want to make sure you know how to do the calculation on there. So 10 factorial, your calculator should tell you 3,628,800. That's the number you should get from your calculator. I think you have to do the stats section for these calculators right here. You have to, where is the stats section on there? Definitely on here. Definitely positive. Oh, see right here, it says probability, PRV. Right there, PRV is probability. And see one of them right here is a factorial button. So you compute the number first, so you go 10, PRV, and then go over to. And then. Yeah, math. Hit number 10, and it's back. So again, and then go over to probability. And the second one comes out. You good? Right hand up. Set it and put it. 450. All right, everybody? All right, so that's our factorial. Nice to meet you right here. Example 1, 6 runners are running a race. How many different orders can they finish? The answer is going to be, oh, sorry. 6 runners are running a race. How many different orders can they finish? The answer is going to be 6 factorial, yes? Or if you're using FCP, it's going to be 6 multiplied by 5 multiplied by 3 multiplied by 2 multiplied by 1, yes? Or just 6 factorial. There are 720 ways to have that race finished. Questions there. So then why is it's not simply 1 out of 720 chance for somebody to win the race? Why is it not simply 1 out of 720? Because some runners are better than others, yes? Right? Right. You're not going to randomly close your eyes and pick an NFL team and say they're going to win the championship, right? You're going to pick from the higher tiers because they will have a better chance of winning, yes? Same thing right here with you don't just randomly pick a runner and say, I got it, man. I'm going to win cash money, yes? Yes. That's cool. Yeah, 720 runs. So I already showed you guys how to do this on your calculator. Let's make an adjustment here. 10 people are running a race. First place will win gold medal. Second place will win a silver medal. And the third place will win a bronze medal. How many different ways can the medals be awarded? Now, is this question asking us about every single runner? It's only asking about the runners who finish in first, second, or third, correct? And so let me ask you a question. How many people can finish in first? 10 people. How many people can finish in second? 9 people. How many people can finish in third? And we stop right here. Because we only care about finishing first, second, or third. Yes? So you multiply those together. What does your calculator say when you multiply these together? 9 times 8, 72. 700. Oh, yeah, it's 720. Huh? 720. Questions there? This kind of calculation is a very common calculation. We often have a group, but we don't want to order the entire group. We only want to order part of the group. Imagine, for example, you're going to Oprah show, and you know it's the big Christmas giveaway show, and they're going to be giving away prizes. Yes? But let's say they're only giving away 5 prizes, and you want to figure out the chance that you win a prize, right? You only need to consider the 5 prizes. So how many people are there for the first prize? One person wins, how many people for the second prize? And so let's say there are 400 people in the auditorium. It's going to be 400 times 399 times 398. I said 5 prizes, right? Times 397 times 396. Those 5 people, that's the number of different ways that they can select 5 people. Yes? Yes? Questions there? This, therefore, is a very common calculation that we have to do. And because it's a very common calculation we have to do, mathematicians have developed a shortcuts to get to the answer. You guys like shortcuts? Yes? All right, so I just did it this way right here using the fundamental counting principle. 10 times 9 times 8 gives us an answer of 720. But there's a different way to do it, a shortcut. And that shortcut right here is called a permutation of our objects of our objects. That's called a permutation of our objects chosen from a total. They should have the word total right here, T-O-T-A-L, of n items. When we have that idea right here of we're selecting only a smaller group, we write this down right here. We write NPR. N is the number. How many people were running the race? 10 people. And how many of the positions were we choosing? 3 of them. And we write this right here. We write 10 permute 3. From the 10, we're only going to do permutations on 3 of them. Okay? From the 10 possible positions, we're only going to do permutations on 3 of them. Questions there? We say 10p3 or 10 permute 3. Questions there? So that means I only have 3 slots, and the first is going to be 10 because there are 10 in total, then 9, and then 8, and you multiply those together. That's what this literally means to do this. All right? But guess what? They don't write that down. They write this down instead. And let's see if we can bridge the 2 gaps, shall we? You do need to memorize this formula. There are, I think, 3 questions on there that ask this formula. But other than that, you can use this button on your calculator. Most of you guys, you have this button on your calculator as well. But before we use the button, let's explain, let's see how it works. So I am trying to calculate, I forgot, I need to close the page first. I am trying to calculate 10 permute 3. And the formula is, let me write up here for us, n factorial divided by n minus r factorial. So my formula is going to be 10 factorial divided by 10 minus, that's not 10, divided by 10 minus 3 factorial. Okay. What I want you to keep in mind is that this formula should give us this. 10 times 9 times 8. That's what this formula should give us, yeah? Yes? That's what it should give us. That's the answer, yeah? So let's work this out. What is 10 factorial? I'm doing the top part right here. What is 10 factorial? It is 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. Questions there about the numerator. Now, what is 10 minus 3? So the denominator is actually 7 factorial, yes? What is 7 factorial? 7 times 6 times 5, 4, 3, 2, and 1, yes? Questions there? Have I lost anybody? I'm just using the formula as it is written. Look carefully. What will cancel from the numerator and the denominator? What will cancel out? 7, 6, 5, 4, 3, 2, and 1 will all. What's left over? Exactly what we need. Yes? And that's how they came up with the formula. Is that they just need a formula to plug into a calculator and say, wait a minute, this will work. Right? If I just do all of them and then I cancel out the pieces that I don't want. Because remember, I only want to go up to 8. Everything after 8 needs to be canceled out. And so that's why this formula right here works. N factorial divided by n minus r factorial. Questions there? Comments, queries, concerns? All right, go ahead and plug N10P3 on your calculator. See if you get the right answer. I think it's 720. Go ahead and type in 10P3 on your calculator. For most calculators, you need to hit the number 10, then hit the button NPR, and then hit the number 3 in that order, and then hit enter one more time. For most calculators, you gotta hit the number 10 first, and then NPR on your calculator, and then 3. Give you 720. I'll wait if anyone needs help with that. And permute R. From my 10 items, I'm going to permute a list of 3 of them. Again, permute means to order. From my 10 items, I am going to put an order of 3 of the items. Questions there? Comments, queries, concerns? Cool. Cool. And so that's what they have written for us right here. NPR, it breaks down to n factorial divided by n minus r factorial. And so there are 6 lifeguards on duty one Saturday afternoon. There are 3 lifeguard stations. In how many ways can the 3 lifeguards be chosen and ordered amongst the stations? Let's do it the FCP way first. How many stations are there? 3 stations. How many lifeguards can I select for the first station? How many lifeguards can I select for the second station? How many can I select for the last station? And then the remaining 3 I send home. I don't care about them, yes? 6 times 5 is 30. 30 times 4 is 120. That equals 120. The other way to solve this using NPR is going to be 6. I have a total of 6 lifeguards. I want to list them, and I want to get a list of 3 of them. I want to permute 3 of them. Type this into your calculator. Let's see if you get the same answer, 120. Questions there? We got it? We got the right answer? We got a different answer? We got the same answer? Yeah? Alright, cool. Yeah, so FCP 6, 5, 4, 3, 2, 1. No, 6, 5, 4. And then NPR 6P3. And that's going to be the same answer, 120. I am paused. Questions there? All right, cool. I already showed you how to run your scientific calculator. Anybody need help with the calculator? Or you're just gonna ask me after class? Oh, you can ask me after class. Hit the probability button, and then you have to find the NPR. All right, so that takes us into our next group right here, and that is combinations. Sometimes we do not care about the order, we just care about the number of groups that we can create. For example, we may not care about which lifeguard occupies the station. We might only care that 3 lifeguards are chosen. Each distinct group of objects that can be selected without regard of order is called a combination. A combination is when you're not using an item one-on-ones, but the order makes no difference to the answer. Let's give you a classic example. Let's say I have 20 people right here, and I want to select an e-board, an executive board, right? Executive board is it's not executive board, so a committee. Now, a committee is 5 people to get together to work, right? I select a committee of 5 people. Does it matter if you get chosen first to be on the committee or last to be on the committee? No, it's going to be the same committee of the same 5 people, right? It doesn't matter which order we pick them. We just need to have it as this is a group, yes? And so what happens right here is when we are looking at a combination, we don't care about the order, we care about the group. Another way of saying this right here is that if I have this right here, A, B, and C, or I have A, C, and B, or I have B, C, and A. In terms of combinations, these are all considered to be the same. The order is different, but it's the same group, yes? Yes? And so for a combination, the order makes no difference in the outcome. It's like saying I'm giving away a prize and everyone that I select gets $100. It doesn't matter what order you're selecting, it doesn't matter, yes? A permutation, on the other hand, the order does make a difference. If the person in first place gets 100, person in second place gets 50, and the person in third place gets 25, the order matters, yes? Right? And that would be a permutation. Question there. To convert from a permutation to a combination requires a single number. When you're going from a permutation to a combination, you add in an extra right here. You divide by r factorial. R factorial is exactly the number of different ways the group can be ordered. So if you divide that out, you cancel out the overcounting of the groups. So to go from, if this R is not here, it's a permutation. Once you remove, sorry. Once you remove the, once you put the R in there, it becomes a combination. You ever heard of combinatorics? This is what they were talking about. Number of ways they can make groups. All right, so we have that right here. And so let's look at an example. At a certain event, 30 people attend, and 5 will be chosen at random to receive prizes. The prizes are all the same, so the order in which the people are chosen does not matter. How many different groups of 5 people can be chosen? Because the order does not matter, and each person is chosen once, the answer is going to be from the 30 people, I am going to choose a group of 5. So it's going to be 30, choose 5. Go ahead and type that into your handy dandy calculator. Tell me what answer you get. It's going to be 30 factorial over 5 factorial times 30 minus 5 factorial. Going to be 30 factorial over 5 factorial times 25 factorial. What does your calculator say?
I got 142,506.
Did we all get that? 142,000? 506. We all get that number? All right, so let's show indeed. NCR, plug it in. And yes, you got 142,506. Questions there? Now let me show you how to do this using the fundamental counting principle. So how many people are being chosen? 5 people. So I forgot I gotta clear that first. 5 people are being chosen. So it's 1, 2, 3, 4, 5. What we do is we pretend like we're ordering the people. So it's going to be 30 multiplied by 29 multiplied by 28 multiplied by 27 multiplied by 26. Yes? And then we divide this number by 5 factorial. Because 5 factorial is the number of different ways these groups can be made. Since a group of 5 people, you divide by that number factorial, and that will give you the same number, 142,000 and change. Although if you type that into Weber's I will not be happy. Questions? Comments? Queries? Concerns? The big thing you have to look for right here is whether or not the order matters. Okay, that switches us from permutations into combinations. Again, you need, that's what I'm asking you right now. I want to see you doing a calculator because you don't want to be at home, Sunday night. Oh, I need to move the assignments back, don't I? I think I have all assignments due on Monday, but they made Monday a holiday. I need to remember to do that. Move everything back. But you don't want to be up Monday night trying to do this thing, and every time you get the wrong answer, right? And so you have to be careful about that. All right. Might be our last example. I don't know. A lottery game consists of drawing 6 distinct whole numbers from numbers 1 through 36 in any order. Therefore, does the order matter? This is a combination question. Okay. Then one more number is selected from 1 through 19. This is often called the Powerball. Yeah. Did I ever play the Powerball? I'm about to show you why you shouldn't play the Powerball. I'll show you why. Yes. If you match all 7 numbers, you win the jackpot, which I think currently is like what, 300 million or something else is like that? $300 million. No. See, that's how they get you. They shout 300 million really loud, but they don't tell you to do the math. Yes. Let's do the math. All right. So we're first going to look how many have 1, 2, 3, 4, 5, 6, 7. Draw a line right here. Out of the 1 through 36, how many options do I have for the first place ball? 36 options, yes? Oh, they didn't write it out. Right? And so therefore, it's going to be 36 options right here. How many for the second ball? 35. How many for the next one? How many for the next one? 33. How many for the next one? And how much the last one? And then you divide all of this by what factorial? By 6 factorial. 6 factorial. If you multiply these, you say it's a huge number. Yes? And then they have the audacity to say, you know what, the Powerball, you got to multiply it by 19 again, because there are 19 choices for the Powerball. You have to multiply it by 19 to get the the number of different possibilities. Yes? Exactly. Check your head and defeat. All right, so again, so like I was saying, this is going to be 36 choose 6 and then multiply by 19. And when you do that, the answer is, let me put the commas in for you guys. Comma here, comma here. The answer is that there are 37 million. The answer is that there are 37 million different combinations to win the Powerball. So my question is how are you going to pick the right one? You know, back in the day, what people used to do, right? Buy every single ticket. If they're selling $2 a ticket and there are 37 million combinations, what 37 times two? 74 million, yes? So you need $74 million. So if you buy every single ticket, you spend $74 million, but guess what? You're gonna win $100 million, yes? And so you're guaranteed to walk away with 24 million, yes? Guess what they did? They passed a law saying you can't organize and buy all the tickets. Because that what used to happen, because it's very, very rare for a person to select the entire thing and win the whole thing. And the number gets larger. When it gets up to like $800 million. That's what you do. You just buy all the tickets. All right. But they don't want that. So they say, yes, let's not do that. All right, we are out of that's the end of 4.3. The unit test is not on Monday, February 8th. It is on Wednesday. What's today's date? What's next week Wednesday's date? The 18th? Yeah, it's on the 18th. I can stick a one right here. There you go. All right, let me take attendance. Let me send you guys on your way. Oh, they got a point right here. If you look on the course, there's a Zoom link right here to the review session. And so you can pull that up. I don't know if you guys remember that for the first step, but there is a review session on there. And also remember, all the questions come from WebAssign, and so you should focus on those WebAssign questions. I think I might take some time, so moving on to the next section. I might take some time on Friday to go over, because some of these permutation and combination questions are actually quite confusing. So I think I'll take some time to go over some of these to make sure we're all on the same page. Hmm. Hold on, so I gotta try again. To permute or to combine? That is the question. We are. That's true. Okay. Broadneck, Brown, Dixon,